So it will take too long for me to do complete analysis of these three programs while you're watching. So I did this separately, and I just want to show you um, a graph or a plot that shows the information that I got out. So these are three programs, remember? So the I have two versions of the recursive program, so either towers or R tower, D tower, and then I also have the Q and T that I got out of OEIS, which is essentially something like computing a big polynomial and extracting some coefficient. And so this is done in three colors. So I have the original program in black, the first one I showed you called towers. And what you see here is three things at the same time for that program. So these are the three types of data that comes from timing the program, from counting the number of entries in the remember table, and from looking at the size of the allocation made by Maple. So you see three graphs in black down here, up here, and up here. Um, this is a log-log plot, so you can see some straight lines, and that corresponds to a power law um, uh, relation between the space or time compared to the number of bricks in that we're counting in the Watson problem. So the black time consumption you see down here, this is the number of entries in the remember table, and this in black is the size of the allocation. Now, the first thing that you notice is that there's some spikes down here, right? Some very dramatic spikes, as you can see. Sometimes it takes much longer to make these computations than other times. And actually, you can see if you sort of follow this up, this is related to the memory allocation because it actually takes a long time to get memory out of an operating system. The operating system has to sort of first clean up the memory so that there's a contiguous number of bytes available and give that to the program. So this sometimes takes some time, and this is exactly what these spikes are about. So this is going to these spikes will happen when the size of the member table gets so big that the program has to ask via Maple has to ask for some extra space. So you can see that there's a very systematic growth. I mean, the beginning, nothing much happens. I'm actually a little bit unsure of what happens there. I don't quite understand, but this is just at the very beginning, so we should probably just disregard it. And then you can see this fairly systematic growth of the size of the remember table, which is reflected in the size of the allocation. But of course, the size of the allocation will go in jumps because uh, the program doesn't sort of continually get more data. It just keeps running until you see, okay, now I hit the top, and then it asks for another unit of space. Probably, most likely, the unit of space asked for is proportional to the size you already have, or something like that. So you don't ask for too little. So I mean, this is more efficient if you can guess the size. And of course, Maple is simply struggling here because we're making generating a lot of data, and sort of keeping track of that is work. But you can also see that the rates of growth are sort of roughly proportional of the three kinds here for this program. Now, then the blue program is the D and R tower, and you can see that this is better on all counts. It's faster, it takes up less space, and this, of course, has to do with two things. In a sense, I'm trading in time for space for time by the choice of having the D tower and the R tower program, and in which the D tower doesn't save anything. Then I'm spending time on looking up something instead of saving it. And of course, that will make my program be slightly slower, but spending less time. But the program is still faster, And that's for two reasons. One is that the program will save some time by using symmetry and so on. And also, actually, dealing with the memory also takes time, right? So that's sort of a secondary thing. My program doesn't have to deal with the memory, but Maple has to deal with the memory. And as the bigger it gets, the more heavy it is to haul around, and that will simply make my program work slower. Now, for the third option, which is the one I got out of OEIS, this is sort of this red-brown color here. There's nothing here in the middle because there is no remember table, so there's nothing that I could gauge the size of. I'm just looking at how big my program, how big an allocation my program will have, and you can see that it behaves radically differently from the other two programs because it gets by. It sort of grows a little bit like the others for a certain amount of time, and then it gets by with that size from that point onwards. And of course, it's a little bit hard for me to say what Maple does, but it's probably being clever in a certain sense because I'm asking for this big polynomial to be computed, and then I'm extracting some of the coefficients. But of course, I don't need to compute the whole polynomial to extract a specific coefficient of it. So most likely Maple has some clever way of extracting only the information that I'm asking for and not computing everything. And I would guess that if we did compute everything, that would grow at the same order of magnitude of what we've seen in the other two programs, but there's something clever going on. Which I cannot really tell you how it works because this was just a two-line program, but behind the scenes there's something interesting going on inside Maple. But you can also see that it's slower, right? So it has a different rate of growth, and it's substantially slower than the other programs that I have, except of course when this time consumption that has to do with memory, dealing with the memory. So of course there's a trade-off here. So this two-line program that we got out of the OAIs, it's very space efficient, but it's not so time efficient. And then of course it depends on my situation, what I should do. Maybe I'm okay with having my program be slightly slower. Remember, this is not so bad as the other cases we looked at. This is a log-log scale. So this maybe runs like n to the 4, but not like 4 to the n, right? So that at least is better. So maybe I could live with a slower program if that means that I can get further without running into the hard limit set by the size of the memory of my computer. But maybe I also, depending on how badly I need these numbers, I could go back and I could see if I could maybe release some memory made by the programs. I think, if I had to, I could probably be a little bit more efficient than anything that you've seen by sort of keeping track of only a certain level of information and then throwing that information out when I'm done with it in the computation. I think that could work. But of course, we still have lots and lots of entries here, so there's no good motivating factor for doing this more complicated. So what you see here is that we can, first of all, so let me just make a conclusion. So first of all, programs, when we deal with how much they sort of cost, there is an issue of time and there's an issue of memory. It's important to notice that the problem with spending a lot of time is different from the problem with spending a lot of memory. With memory, if we have the data, if we have the memory cells to run the program, we usually don't care if we're using half or 2/3 of the data that we have, but we of course care about hitting the hard limit. With time, it's different. We can negotiate about how much time we want to spend within reason, of course, but is it a question of a minute or an hour or a day? We can probably deal with having that. So we're a little bit more flexible there, but of course, then we always want it to be fast because we don't want to sit around waiting for the data to come out.